All right, so that was a successor representation, which are a tabular method. It means you need to have a matrix linking all states to all states. So of course, that's not possible for realistic applications because because of dimensionality. If you have too many states, then you need n square values, and that just explodes for most problems. And that's only possible if you have discrete states, of course, rows and columns of a matrix. If your states are continuous, like in cardpole, you cannot do that. So we need to do function approximation. We'll do linear function approximation first, and then see how to do it deep. That's really the same story as before. So we are going to represent a state not as a one hot vector. It's one if I am in that state, zero otherwise. Could be a huge vector and have a big matrix, but use some features as eyes, as ears, as whiskers if you're trying to describe a cat. So really function approximation, we can construct that vector as we have seen in the lecture on function approximation, or learn it with an autoencoder. That would be the latent space of an autoencoder, as we have seen already in model-based. So again, nothing new here. When you do that, the algorithm is called successor features or successor feature representation, SFR, where actually what the SR is going to represent is not how soon will I see a state, so discounted by gamma, but how soon will I see a feature. So what I predict is not if I'm going to see a cat in the close future, but I am going to see eyes, I am going to see ears, I am going to see whiskers. Per feature, you predict if you're going to see it. So we are going to note the successor feature in that notation. So either we steal the matrix M, which depends on the policy for state S, where you are right now, and you ask yourself if you're going to see a feature J, for example, ears, in the future using your policy. Could not like that. Am I going to see the feature phi J using my policy when starting in S? It's the same definition. I mean, S eventually takes the action if I want to. The sum from now until the end of time of the discounting rate to the power of time, and whether I see the feature J in the state st plus k. So instead of counting if I am in the state, I count if I see that particular feature. So for linear approximation, there was this paper by Gehring in 2015, says that you can linearly approximate the SR for a feature J based on a feature representation of your state. So you linearly predict whether you are going to see ears in the future from the description of your current state. As a linear approximation, you just need these weights to be set to the right value. And then the value of a state is the sum over all features of whether you're going to see that feature in the future, the SR, times the reward associated to that feature. So the SFR matrix associates every feature to every feature. I'm not talking about states anymore. And it says that if I see a kitchen door in the current state, how likely will I see a food outcome in the near future? It's not linking states with states, but features with feature. If I see something of that color right now, what does it mean about how close are features of another color in the future? So that's something that can be very dense, but we can learn it, we will see. And then for each feature, you must just learn how rewarding they are. If I see food, how good it is. If I see water, how good it is. If I see something sharp, how good it is. I may get hurt with it. So you don't assign rewards to states or transitions, you assign reward to features. Something in that scene is rewarding, and that's what this immediate reward means. That means a good state is a state where I'm likely to see good features in the near future, which are associated with high rewards. If I can predict that I will see some food very soon, then that means I am in a good state. So the formula is not very important. You can put it in a matrix vector form. It's just linear approximation. You have a vector of rewards for each feature. A matrix that says predicts how close are features from each other, and the feature representation of your current state. So you're in that state, you predict which features you are going to see in the future, and then you compute for each feature how much reward they contain. Sum all that, but one value, the value of your state. Once again, that's the cool thing about successor representation, that ensures transfer learning. What you learn in M is how close are states or features, in that case, from each other. If I see a door, then I'm likely to see food behind that door. How rewarding are the features can be learned totally separately. That means I can set goals, so I have goal conditioned RL, as we saw in TDM, saying that I'm learning transitions in that grid world, and with a certain reward for each feature. For example, the features are the location where you are. That says I want to be there. So I get rewards when I make a transition to that state. So I can learn a policy like that with that value and then train an actor. But if I change the reward function to get another reward vector here, and says only transition bringing me to this state are rewarding, well, I just need to relearn R. I don't need to relearn M, because that's just how close am I from that state. The transition dynamics are abstracted here. The reward can change, and we can very quickly recompute the value of everything and recompute the policy. That allows transfer learning between different reward functions in the same environment. You can define multiple goals very flexibly by just modifying this vector R. So we still need to learn that matrix, and we will use exactly the same kind of TD-like learning rule. So the error is I want to predict which feature I am going to see in the future after being in the state ST. So I take my feature representation and apply the matrix M on it. That's supposed to predict which feature am I going to see in the future. And I compare that to the features of the current state if I'm already in that state, plus gamma, the features I'm going to see in the future after being in the next state. Still a TD-like error. Reward plus gamma, value of the next state, minus current prediction. Except here we are predicting the visits to features. And then we can update the whole matrix column per column. Well, that's the same idea as R for linear approximation, that you can linearly predict the SR from the features. But that only works, of course, for a fixed feature representation, as we saw in the linear approximation lecture, and not for deep ones. So you cannot backpropagate through anything here. So we need to go deeper, and that's what the next part is about. So it's one paper by the group of Sam Gershman, which was influential into bringing successor representation back to light. So it's an old idea by Peter Dayan in 93. But Sam Gershman did a lot of work in the context of neuroscience to explain that SR is a better model of reinforcement learning in the brain than purely model-free or purely model-based approaches. So here is the deep network that they proposed in their paper. So deep successor reinforcement learning, which is just an extension of what we saw before on function approximation. What you do is that you are in a state st at time t. It could be an image, so you could have a CNN, which learns to produce a vector, a feature representation of that state using anything. So here it's a CNN, but it could be really anything. If you want this representation to be meaningful, a good representation of your state, then you need a decoder so that you can compute a reconstruction loss between your current state and its reconstruction. And the latent space of your autoencoder will be a compressed version of your initial state. So you have here an autoencoder. From this latent representation, phi of the state, we are going to predict how much reward do you get in that state. The immediate reward function, and it's a linear function. You have a weight vector W, and you make just dot product between this vector with 512 elements and this reward vector with also 512 elements. That gives you one value, how much reward you get. And then for all actions which are available in your problem, for example, going left, right, up, down, you have 4 branches, so 1 branch per action, where you are going to predict the successor representation after being in that state and taking that action. So which features, in terms of latent representation, am I going to see if I'm here and take this action? So I predict the latent space, latent representation of at different time scales. So each element of this vector is predicted as a successor representation. How likely am I going to see this value for the latent space? And that for each action. So that's the structure. We have 4 things to learn: an encoder, a decoder, a reward prediction, and the SR itself for each action. So you have your encoder with some weights theta, your decoder with weights theta hat in the paper, and you just minimize the reconstruction loss. So for example, the L2 loss between your current state and its reconstruction. So a classical autoencoder, it's not even variational, it's just pure autoencoder. And then you linearly predict from your feature vector how much reward is associated to it. So you compare the reward you get after being in the state ST to your prediction, which is a linear regression. On average, on your training set, it's off policy, we will see, so it could be a replay buffer. So the mean square error between the rewards and the linear prediction. So they do both. Of course, if we don't have the autoencoder, so the decoder part, these representations here would specialize to predict rewards. So forcing it to be an autoencoder makes sure that these representations contain information about the world itself and not only about reward. Otherwise, it would be too reward-oriented. We will see that the trick is that this vector W, we are going to learn it for particular task, but we don't always need it. We can just swap it depending on the task. And so then you need to predict the future feature occupancy, the SR, when you are in a state S, take the action A, how far are you from the features of the future state S prime? Something that is noted like that. So for each action, you have a vector taking your current state as an input, and it has some weights alpha. So you have It's noted like that. So F theta is your encoder, G theta tilde is the decoder, W are the weights for the rewards, then U alpha, it's all these different predictions which predict a latent representation after each action. So if you're able to learn that, the Q value of an action is easy. It's how much reward each feature brings times how close they are after taking that action. And that's the SR. Just vector matrix multiplication. So just simply do it. You have your Q value per action. And you don't even need an actor because you're learning Q values. Just pick the one with the highest Q value. So you get n vectors if you have n actions. Take your vector W here, compute the dot product with all of them, then argmax, or some epsilon greedy around it, and that's your action selection. It's really DQN-like. You can compute a Q value from that, and then with these Q values, you just act. So you're model free also while acting. The SR of each action is learned, so these weights, of course. You take your SPE, features of the current state, plus gamma, features of the greedy action in the next state, minus SR in the current state. So it's really Q learning like SPE, meaning that the next action that you take is the one who has the highest Q value. Here it's a bit of a shortcut. It's not the maximum SR, it's the maximum Q value, which is computed from the SR. It's more shortcut, but you get the idea. It's computing using a target network, alpha prime, so past value, just like in DQN. And when you minimize this loss, it's only with the weights of the SR. You're not learning end-to-end, so modifying the encoder when you try to learn your SR. It's just a small trick. So we have 4 sets of weights, and you learn them in 2 phases. So first the encoder, decoder, and reward, and then only the SR, or successor features. And your combined loss functions is learning these 4 weights, reconstruction loss, reward loss, and successor feature loss. So here is the algorithm as I published in that paper. So it's of policy. We have a Q-learning-like algorithm, so we can use a replay memory. We initialize some target networks, and then we are going to do transitions, sample actions based on the Q values, store them in the replay buffer, sample mini batches from the replay buffer, minimize the different losses, and loop and loop and loop with annealing for the expression variable, so epsilon greedy action selection. So it's really DQN, except that you're not learning directly the Q values, but the successor features combined with that weight vector give you the Q value. That's the important formula. And so they applied DSR on a simple grid world when you want to pin that goal. Then after a while, the goal changes. And you see it's learning similarly to DQN. So of course it's 2016 compared to DQN. And it's more fair to compare it to DQN because it's really the same kind of algorithms. If you use other tricks, and of course going to be better. And on a Doom-like engine, so VisDoom, where you can apply RL, they design an arena like this, where you have to move in this 3D world to get a reward that will be here initially. So you learn just based on raw pixels to go to that direction with a lot of steps. Of course, the time is very finely discretized. It's quite complex things when you only have images as inputs. And you see it's working just as well as DQN. in terms of performance, it's not impressive, except when you change the goal. Like here, you can learn to always go left, and the QN can do it. Then after a while, you put a reward in another room. How quickly can you adapt? Well, they showed that the only thing you need to do when you change the goal is to learn the small weight vector W, the one that is here. So when there's a change in the task, you're not going to change the encoder, the decoder, or the successor features. Just have to relearn this small vector with 512 elements, and you don't need that many samples to relearn it. That means you can really adapt very quickly to a change in the reward distribution, while DQN needs a lot of time to readapt to a change in the rewards, because you need to relearn all Q values in all states in order to adapt to that. While it's almost immediate in DSR, that means you can learn the SR of going always left, then you put it on the right. It will take a while to change the small vector W, but not very long. Then you can put it back there, just put back the weights W corresponding to that task, and then it's going to work out of the box. So that's really the cool things that allow transfer learning and also latent learning. That means you can let your agent act totally randomly and learn the SR in the environment without any reward, just discovering what happens if I do that, how close am I from that state. So you just learn the successor features, and only later you introduce rewards. It's called latent learning in animal psychology. It means when you train a rat to move in a maze, you don't put it right away with the task. Just let it get used to that maze, smell a bit everything, know where is what, where to turn, and only then you introduce rewards to see how it learns. And you can learn much faster if you're already used to your environment, you know what happens, without having a task in particular. Then when comes the task, you can really reuse your knowledge, which was totally unsupervised, not even reinforcement, to go faster when you need to acquire a specific reward-related behavior. So that was the idea why it was interesting for neuroscience, because the successor representation is a form of cognitive map of your environment. You learn relationships between things in the world without being goal-oriented. You don't need to get rewards to learn. Just experience things in a kind of unsupervised manner. And when comes the time that you need to solve something, you use that knowledge. So that's what the hippocampus in the brain, for example, might be doing. A lot of papers which have been linking successor representations to the function of the hippocampus in reinforcement learning in the brain. So now there are many deep variants of the successor representation idea. And actually, 3 papers were published exactly at the same time in different conferences, containing almost the same idea. So here I explained the paper by Sam Gershman and Kulkarni. But DeepMind published a very similar architecture, and also a group in Germany. So it's hard to say who is the first to do this. It's just straightforward implementation of successor implementations with function approximation, except it's deep networks. So we don't know who should get the credit, but it doesn't really matter. And now, just for fun, so the idea of deep SR has been used in that paper that does visual semantic planning. And I think the application is really, really fun and impressive. It's really based on that idea of the DSR algorithm. You will see a slide. They did a video which is very well made, so I won't do the explanation, just let them explain what they did.
In this video, we introduce our work Visual Semantic Planning using deep successor representations. Given a task and an initial configuration of a scene, our goal is to learn a sequence of actions to complete this task. We explore complex, multi-step tasks such as finding a bowl in a kitchen and putting it in the microwave. We extend the AI2 Thor framework to enable rich interactions with objects. Our agent can interact with the environment via 7 high-level actions. Some actions take arguments of either a location or an object. These actions are navigate to a point, look up and look down, open or close a container, pick up an item, and put an item down in or on a receptacle. Given the agent's visual observation and internal state, our goal is to produce a plan that results in the completion of a task. Our model generates these plans by estimating the Q value, or the expected value of future rewards, for each action. We use the successor representation to decouple environment dynamics and reward functions. This decoupling enables task transfer. When adapting a trained network to a new task, we simply retrain the reward predictor while fixing the successor features that summarize the dynamics. Now, we show qualitative results of our method as well as several baselines. We evaluate our method on 3 levels of difficulty. Difficulty is based on the length of the optimal plan and the amount of randomization. These tasks involve changing object states, collecting objects from multiple locations, and finding an object in a random location and bringing it to a receptacle. Here, we show all models attempting a hard task of searching for lettuce in the scene and putting it on the table. Compared to the baseline methods, our model is able to complete the task with the fewest steps. In the medium difficulty task, an agent must collect several objects from multiple locations and bring them to a pre-specified final location. In the easiest task, the agent must navigate to a target location and open or close a specific door. Our successor representation lets us transfer to new tasks quickly by only retraining the reward predictor. Here, we provide an example of policy transfer. In the original task, we trained our model to find a bowl and put it in the sink. When transferring the policy, we retrained the model to search for an egg and put it in the sink. We compare training the reward vector with training the entire network from scratch. Given the same amount of training data, our model can adapt to the new task with a much higher sample efficiency. For quantitative evaluations, please refer to our paper.